Hey everybody, welcome to our third webinar here with Target Test Prep. This is the first one of the new year. As everyone can see, we decided to do divisibility tonight. So this is our third after we've done critical quadratics and unit digit patterns. For anyone new to the webinar series, this is going to be ongoing every Tuesday. And we decided when we started this webinar that we wanted to make each webinar on a detailed topic. As those who are using our curriculum know, we have a pristine level of detail on what we've included in the curriculum. And for those who haven't used it yet, I would invite you to try it out to see why everyone's been so happy with it. We did spend a lot of time. We wanted to make sure the detail was there, and this is what Scott and I decided to do for our webinars so that everyone could leave each webinar feeling like they have one topic checked off their list or close to checked off their list. And if anyone has any questions about this webinar or anything we're speaking about tonight, feel free to reach out to either Scott or I, and we would be happy to chat with you about anything, including your GMAT. So with that said, tonight we are going to start off with some divisibility using some data sufficiency principles. I'm going to be doing some questions first. Scott will be around to answer any questions that you guys have. And, as always, we'll give you about 2 minutes to answer each question. And I would say we're going to dive right in here. And I'll give everyone 2 minutes for the first question. And this is going to be a question involving data sufficiency with divisibility. So the first question here is up on the screen. If x is a positive integer, is x a multiple of 12? Certainly, as everyone answers the question, you can start to put in your answer into the chat box. And as always, I'll walk through the answer once everyone's done. So we can start with 2 minutes on this question here. Okay, everyone, so that was actually a little over 2 minutes. I see that went by very fast. Now, I didn't see anyone punching their answer into the chat box, so I just want to make sure everyone had enough time to go through that question. Scott, unless you're seeing any answers, I did not see anyone enter anything in. So I will go through the solution now. So this question here is certainly a common type of question you could see on the GMAT in data sufficiency. It's a divisibility question that's asking if X is a multiple of 12. Now, there's two ways to look at this. You could look at it in the sense of how it's written. Literally, is it a multiple of 12? Another way to write this is X over 12 equal to an integer? Because the reality is if 12 divides into X evenly, then that would mean that X is in fact a multiple of 12. And keep in mind too, and we've talked about this in past webinars, that this is a yes/no data sufficiency question. So in order for something to be sufficient, you're going to need either all no's or you're going to need to get all yeses. So in statement one, there's a lot of different ways you could go about it. You know, when I've worked with students in the past, a lot of times they've decided or thought that maybe priming out is the best thing. But sometimes simple is the best method on the GMAT. And so when I read statement one and I see that X is a multiple of 6, I think to myself, well, I could probably just make a list of integers of X to see if I'm getting consistent yeses or if I'm getting consistent no's. So the first positive multiple of 6 is 6. And all we have to do is use that value of X to answer the question, is X a multiple of 12? So you could rephrase that to say, is 6 a multiple of 12? Well, the answer to that is no, 6 is not a multiple of 12. Now, the key here is that you don't stop there, that you keep going. And logically, I would say the next step is to take the next highest multiple of 6, which is 12. You say, okay, is 12 a multiple of 12? Well, right away, we can see that the answer here is yes. So we've gotten a yes and a no answer. And if we're doing our grid of A, D, B, C, E, we see that statement one is insufficient, and those answers are not correct. So we move to statement two. Now, the good news is we can take the same exact process here, except this time X is a multiple of 18. So in the same way, I would say X equals 18 as an option for X. Is 18 a multiple of 12? No, it's not. And then we do the next one, which would be 36. We say X is 36. Is 36 a multiple of 12? Yes, 36 is a multiple of 12. So that's insufficient. So B is out. Now the good news is when you look at these together, there isn't really a whole lot you have to do, because the values that you've already selected in statement two will also fulfill statement one. So X equaling 18 fulfills both statements, giving us a no answer. X equaling 36 fulfills the statements, but it gives us our yes answer. So because we have a yes and a no, the answer here is E. So remember, everyone, although sometimes we think that there always has to be these little tricks or things that you have to do in GMAT questions, sometimes something as simple as this can be used to answer a question of pretty decently high difficulty. So moving on, I want to do another data sufficiency question with divisibility. And this is a question that I will preface that it has more bark than it does bite. So what that means is it's probably going to seem harder than it actually is at the end of the day. So let me put this up, and I'll give everyone 2 minutes. And again, as you get your answer, you can start typing it into the chat box. Okay, so that was 2 minutes again. Do you see we have one answer here? So let's run through this as well. We know that n and m are integers, and we want to know if n over 3 is an integer. So we can kind of take the reverse of this question with what we did last time, and we could rephrase it if it helps anyone to say, is n a multiple of 3? Now, one way may resonate better than another, so either is asking the same thing. It really just depends on, what you feel comfortable with. Now, the one thing that everyone should recognize in GMAT divisibility questions, in data sufficiency especially, is that the GMAT is always trying to push you down a path. And if you go down their path, it's probably going to take you a lot longer than if you go down the clearest path and the most simplified path. So what I mean by that is if you ever have the opportunity to simplify, you want to take it. So first and foremost, we look at statement 1. Well, in statement 1, I see that I can divide both sides by 6. And when I divide both sides by 6, I get 9n equals m. Now keep in mind, n and m are integers. And what a lot of people do in this problem, which is a mistake, is they try to divide the 9 to the other side, thinking that that's going to tell them something about n, as in Nancy here. So instead, what I find to be a little easier is to just say 9 times n equals an integer. That way, what we know here is that n literally can be any value. It can be 1, it can be 2, it can be 3, and I could do this all the way on till whatever. Point is, we don't know if n is a multiple of 3 with statement 1, and notice we've gotten there by making this as simplified as possible. Now, statement 2 is no different. I have 32n equals 12m, and the first thing I'm going to do is divide everything by the biggest value I can, and that's going to be 4, giving me 8n equals 3m. Now, in following what I did in the last statement, well, I'm going to get to that part, but before I do that, I'm going to bring the 3 over to the other side by dividing it. The reason I'm doing that is because, remember, we care about what divides into n. So by bringing the 3 over, we have 8n over 3 is an integer because I changed the word or the variable m to integer. So now we get to analyze 8n over 3 pretty thoroughly. Now remember, what we know is that we've simplified everything out as much as we can. We know that the value of 8 times n over 3 has to equal an integer, meaning 3 has to divide into 8n. We also know that 3 doesn't divide into 8, nor does it simplify with 8, leaving us with the fact that 3 must divide into n, and thus n over 3 is an integer, or in other words, n is a multiple of 3, leaving us with an answer of B as in boy. So what I want to do next is I want to get into a little bit of factorials and divisibility, and then Scott's going to take over to do a few more advanced questions on some different types of divisibility things. And factorials is one of those funky things on the test that you can see it in a lot of ways. For sure, number properties is one of those places. And so I want to teach everyone kind of a really cool way to deal with a problem like this. But first, everyone can do it out any way they see fit. But keep in mind, this is dealing with factorials and divisibility, even though you don't see a factorial listed there. So I'll give everyone 2 minutes, and then we will move into the solution. Okay, so that was a little over 2 minutes again. And keep in mind, everyone, that these questions that we're doing tonight are definitely on the advanced side of the spectrum, but they're all very good questions and questions that you'll see can actually be solved in a pretty short amount of time. So what we have here is this is saying what is the largest value of n such that 3n divides evenly into the product of the first 25 positive integers. What everyone needs to remember is that the product of the first 25 positive integers is the product of the first 25 integers is actually 25 factorial. So the way that we can set this up is 25 factorial divided by 3 to the n must equal an integer, and we need to know what the max value of n is. Now, there are two ways to do this. One is kind of a more long-winded approach, and we'll start with that. And then there is a pretty cool shortcut that I want to show everyone that can be used in situations like this when we have a factorial on the top and we have a prime number in our denominator here that we're dividing by, like a number 3. So our goal is to figure out how many 3's can really divide into 25 factorial. So at a bare minimum, we know that the only values we're going to care about within 25 factorial are those that are multiples of 3. So for instance, as we're counting down 25 factorial, we can ignore 25, we can ignore 22, we can ignore 20, et cetera, et cetera. So as we write out these values or these multiples of 3 in 25 factorial, we have 24, 21, 18, 15, 12, 9, 6, and 3. Now, remember, 24, if you were to break it into primes, would break down to 2 to the 3 times 3 to the 1, meaning there's only one 3 in 24. Now, I wouldn't recommend breaking everything down into primes the way I just did with 24 because it's probably going to take a decent amount of time. So if you can kind of eyeball these values but still write how many primes of 3 you see in each one, you should be able to pretty quickly get through this. So 21 has 1 prime of 3. 18 has 2 primes of 3 because it breaks down to a 9, which is 3 squared. 15 has 1 prime of 3. 12 has 1 prime of 3. 9 has 2. 6 has 1. And 3 has 1. So if we add these up, 1, 2, 4, 5, 6, 7, 8, 10, we see that the max value that n can be is 10. Now, as I said before, there is a slight shortcut that will help you, especially if the factorial you're dealing with is much larger than 25 factorial. Let's say it was 150 factorial, for instance. Well, it would take a lot longer to break down 150 into all of the different multiples of 3 and then figure out how many 3's are in those multiples from a prime factorization standpoint. So the shortcut's actually pretty simple. You take the factorial that you're dealing with and you drop the factorial. So it becomes 25. You take the value in your denominator, which again, in order for this rule to work or this shortcut to work, that value has to be prime, and you divide it in. So we can say that 3 goes into 25 8 times. Now keep in mind there is a remainder, but we can ignore that remainder for the sake of this shortcut. We then bring the 8 down and we then divide that by 3. 3 goes into 8 twice. And then of course if we wanted to, we could divide 2 by 3, but we know the quotient of that is actually 0, so we can ignore that. The last thing you do with these shortcut is you sum together the quotients that we just got, 8 and 2, that is 10, and that is your answer. Notice they match. Now, if you want to practice this shortcut on your own, I mean, first of all, we have many, many questions in our curriculum on factorials and divisibility, but otherwise, take any number you want, make any prime you want in the denominator that you would be dividing it in, and do this shortcut. And if you want to practice that and make up some of your own questions and you want to be certain you got it right, do that, email it to me, email it to Scott. We'll confirm you've done it right. But I can tell you this is definitely a high-level question, and if you can get this right in, let's say, 30 seconds or less, that's going to do wonders for your GMAT score. So with that said, I think this is probably a good place for me to stop, and I'm going to let Scott take over, and he has some really cool questions that he's going to give you on the other spectrum of divisibility, and you know, we'll keep going for the next half an hour. So Scott, are you ready to start some of your questions?
Oh yeah, all right, Jeff. Thanks a lot. Hey, good evening, everybody. Thanks a lot for coming, and Happy New Year. Hope everyone's year is off to a great start. One of the things that we're going to continue to harp on, and we've done it in the last couple webinars, is the idea of simplicity. And Jeff has shown you a lot of really high-value grains of wisdom tonight about simplicity. So remember that most people look at the test as this complex animal, and no one's going to take away from the fact that the test is difficult to start. Okay, it gets easier the more you practice. But the key is you got to look for the simplicity within the complexity. Remember, you only have a couple of minutes per question, which is kind of good, right? Because it means you are not expected to bust out a lot of crazy math. Right? Everything is logic-based, and there are efficient ways to solve problems. So whatever you're doing, including the following problems we're about to do, I want you to always ask yourself, what's the simple way of doing this? How can I piggyback on something else I know or something else I've already seen in order to make this problem go more quickly? So, as you know, one of the things that does make the test difficult is there are numerous ways of presenting one concept, right? Just because you can do one divisibility problem doesn't mean you can recognize it in a more disguised form. So what I'm going to do with you for the next half hour is show you a mix of problems that require you to think a little bit more outside the box in terms of divisibility. Okay, so why don't we start with this guy here. We'll set the timer for 2 minutes, and then we'll discuss him. Why don't you start now? Okay, guys, that's about 2 minutes. We like to say it goes by quickly. So what we have here is if x, y, and z are positive integers such that y is equal to 24 times z minus 4 times x, which of the following could be the value of y? Now you could plug in numbers, you can test those numbers out, and you could probably get the answer, but there's a much better way, and a way that will teach you more about the essence of the GMAT. So we talked a lot about factoring, and you can see in this very simple equation that you have the opportunity to factor. Okay, what we can do is we can take 4 out of the right side of the equation, and we'll be left with 6z minus x. A very simple step, and so many students miss this, okay? What I want you guys to see here now is y is equal to 4 times something in here. I wouldn't even care what's in there. We know that z and x are both integers. So we'll put an integer inside of the pink box, right? So what we have is y is equal to 4 times some integer. Well, if you think about what that means, it's really simple. What it means is that y must be a multiple of 4, right? Because y, think about how y is constructed. Y occurs from taking the number 4 and multiplying it by some other integer. Okay, so we look up at the answer choices, and we see that only one of these numbers is a multiple of 4, right? Only 28 is a multiple of 4. So 28 is the only number of those 5 that could be the value of y. Okay, so we're looking for simplicity here. If y is equal to 4 times an integer, y must be a multiple of 4. Only 28 in this example is a number, an answer choice that's a multiple of 4. Okay, the heart of this problem is divisibility. Okay, let's try another one. Okay, this one's going to be a word problem, but you know the little hint here is it's really a divisibility problem at the heart of the matter. So let's give this guy a try. We'll go for 2 minutes starting now. Okay, guys, that's a little bit over 2 minutes. Give you a little bit extra time on this one. This is usually challenging to most students if they haven't been indoctrinated to this strategy yet. So it says, if the original mass of an element in grams is a whole number and the element has decayed by exactly 94% in some time period, which of the following could be the final mass of the element after the decay has occurred? So, you know, part of the difficulty with word problems is organizing your information. And if you can become good at it, everything else gets so much easier. So let's define a couple simple variables here. So let's say that n is equal to the new weight of the element after it's decayed. And we'll say that W is equal to the old weight just prior to the decay. Now, as you know, it's really important to be fluid with percentages and percent changes and percent increases and decreases. But think about this. If something decreases or decays or reduces or goes down, or any other word you want to use, by 94%, the key to ask yourself is, what's left? Well, if you had $100 and lost 94 of them, you'd be left with $6. If you had 100 pieces of a pie and you lost 94 of them, you'd be left with 6 of them. So a 94% reduction is the same thing as having 6% remain. Okay? So guys, what we can say very simply is we'll say that the new weight is equal to 6% of the old weight. Just remember, guys, percent means divide by 100. So not to get off topic, but just so you see what I did there, for example, X% would be X over 100. 12% would be 12 over 100. 1/1000th of a percent is 1/1000 over 100. Okay? So the new weight is equal to 6% of the old weight, and as Jeff told you nicely in a prior problem, anytime you have the opportunity to simplify, you should. So what we can do is we can say that the new weight is 3/50th of the old weight. Okay, just reduced by 2, top and bottom of the fraction. Okay, so what we're going to do here is I'm going to solve this for W. So we can see here that W is 50 times n over 3. Now, if you're not using our materials or you're new to the GMAT, you may say, well, great. So what the heck was the point of doing that? Doesn't seem like we've made it very far into the problem because we have 2 variables and an equation. Doesn't seem like there's much that's telling here. But those of you who have come to past webinars or are using our materials, you realize that this is powerful information on the GMAT, okay? And it's not so apparent to most people. Think about it. If W and N are integers, well, this fraction on the right-hand side can't really exist as a fraction. That 3 has to be absorbed or soaked up or divided into whatever technical word you want to use into the numerator. Otherwise, we're going to have a fraction. We're not going to have a whole number, okay? So, sure as heck, we know that 3 ain't going to divide into 50, right? 3 is not a factor of 50. So 3 will not divide into 50. Another way of saying that is 50 is not a multiple of 3. So what's the only way for this fraction to reduce itself? Well, is if it's the 3 can actually be absorbed by the n. Right? If the 3 won't divide into the 50, the 3 has to divide into the n. Otherwise, this will not reduce to an integer. So what that allows us to conclude in our mind, the 3 dots mean therefore or in conclusion, n must be a multiple of 3. Okay, remember this is a logic test by and large. okay? So if n must be a multiple of 3, just as we did in the last question, we're going to evaluate our answer choices and say, is there one that's a multiple of 3 and 4 that are not in classic GMAT fashion? Well, probably. 32 is definitely not a multiple of 3, 31 is not, 29 is not, 28 is not, but 27 is a multiple of 3. So it's the only possible answer that could be true. Okay? Now, this question always sort of makes me scratch my head because you say to yourself, well, couldn't anything decay by 94%, so couldn't any of the answers be valid? And the answer is no. Mathematically, we see that all of the answers are not valid. Okay, so don't ever judge a book by its cover. And this brings me to another important strategy for you guys. Make sure you're doing 80% of the work on the page. I mean, obviously, you're always thinking, but most of these questions are going to require a reasonable amount of ink. So you would never want to just look at this and then eyeball it. So don't be doing the mental math game. It's going to hurt you every time. Okay, very good. Let's try another one that's going to piggyback on this guy. This one's a little more difficult, I think, because it's in the form of a data sufficiency. So why don't we give this a try? Let me set my iPhone. Let's give it a try starting now, 2 minutes. All right, guys, that's actually about 2 minutes and 30 seconds. It's a tough problem. I want to make sure you had enough time to work on this. Now, listen carefully, because can the answer choice be C? Yeah, of course it could, right? And C comes up just as often, I would say, as anything else, right? But I always want you to ask yourself, especially on a data sufficiency word problem, if you're going to choose C, again, I'm not saying don't choose C. I'm not saying it can't be the right answer. We all know it can. So make sure you're getting the message correctly. Just ask yourself whether you're falling for a trap you shouldn't be. Okay? Just ask yourself that question. Am I falling for a trap? Is it A or B? And I think this question will illustrate what I'm saying nicely. So we have this person, Chanel. She purchased $9.90 worth of pencils and erasers. Now, the GMAT means what it says, okay? So we have pencils purchased and we have erasers purchased. We want to know how many erasers did she purchase. Okay, so we can simply let a number of erasers be E. How many of these guys has she purchased? So we're looking to see whether we can actually come up with an actual number that won't change, so a set number. Okay, and while we're at it, let's let P equal the number of pencils that she purchased. Okay, statement 1. Each pencil costs $1.10 and each eraser costs 80 cents. Well, let's decode this into a word problem. Into an equation. So what I would say from statement 1 is that if you multiply $1.10 times the number of pencils, right? That's the total cost she spends on pencils. And then if you multiply 80 cents by the number of erasers she purchased, right? 0.8 E, that's the total cost of all the erasers. This is going to have to sum to $9.90 because the STEM tells us it has to. Okay, now at this point in time, students immediately abandon statement 1 and they say, you know, neither A nor D can be correct because statement 1 has 2 variables and 1 equation. Well, you can't follow the rule. Like we've all been taught since high school that, you know, you need 2 distinct equations if you have 2 distinct variables, but it's kind of a lie. It's a lie in a sense that equations can be inherently designed with logical restrictions, right? And this is one such equation, and I'm going to show you what I mean by solving this, okay? So what we can do, and this is something that's going to take a little bit of time for you guys to get used to, but remember, factoring is really important. And there's a million ways to solve this equation. I'm going to show you a sophisticated way to do it. Doesn't mean you have to do it. It just means if you could, it's going to save you a lot of time. So I am going to bring I'm going to switch the equation. But what I'm going to do is I am going to bring the $1.10 over to the side of the 990. And most students say, well, what's the point of doing that? The point of doing that is, although it may be difficult to see, they share a common term. They share a common factor, okay, the 990 and the 1.10. Okay, and that common factor is 1.1, right? Because we could pull 1.1 out from the left side of the equation, and we'll be left with 9 minus P inside of the parentheses. That's still equal to 0.8 E. Okay, now just remember here, guys, it's easy to check whether you factored out properly, because if we run the 1.1 through back to parentheses, we're going to have to get back to the line before it, and we will. Okay, we will. Okay, so what we could have done and what we'll do now is we can actually multiply the whole thing by 10, because we typically don't like working in decimals if we can create whole numbers. So by multiplying each of the terms by 10, this simplifies dramatically, I think, to most people's eye, to 11 times 9 minus P is equal to 8 times E. And you could do that simplification in any of the steps. I actually probably should have done it earlier on in the problem, but at any rate, we've done it now, and you see that's much simpler. Okay, so what can we do? Well, take a look. We can solve very easily for E. That's 11 times 9 minus P divided by 8. Okay. Now, here's the point in time where most untrained students say, well, great, why do we do that, Scott? Why do we just bring this equation down to this form where we still have 2 variables, right? We still have the E, We still have the p. What good does it do us? Remember, it's a logic test. Okay, it's testing math, of course, but math is logic. Logic is math, right? So what does this mean? Okay, let's think about what this tells us. Well, we know that you don't get pencils or erasers, at least in this problem, in fractional values. They're whole numbers, they're integers. Well, we need e to be an integer. Okay, well, what does that mean? It means that the fractional component on the right is going to have to be reduced. That 8 can't linger in the denominator, or we're not going to get an integer. Well, so that means the 8 has to be absorbed up into the numerator, and you guys can see, sure as heck, the 8 is not going to divide into the 11, right? 11 is not a multiple of 8. 8 is not a multiple of 11. So 8 is not going up into the 11. So all that's left is for the 8 to divide into the quantity 9 minus p. Right? If 8 does not divide into 9 minus p, something's wrong with this problem, right? Because there's not going to be an integer value. There's nothing wrong with the problem. Saying, for example, right, if 8 didn't divide into 9 minus p, it wouldn't work. Okay, this problem couldn't be true. Okay, so then we're kind of at the last stage of the problem. We want to know, what does that mean for the value of p? Okay, how do we make 9 minus p divisible by 8? And what we can see here is the only value that would work is if p were equal to 1, right? Because then that would be 11 times 8 over 8. The 8s would cancel, and we would see that e is equal to 11 and p is equal to 1. Okay, and if we refresh our memory of what we're being asked, we want to know, how many erasers did she buy? And of course, the answer is 11. Okay? So again, don't think just because you have one equation with two variables that it can't work. If there are inherent logical restrictions, many times number property restrictions, here divisibility, two variables or one equation will work. Now, just so you know, what I'm doing data sufficiency, I'm going to solve them out so you get the most learning. It's up to every individual to decide at what point in a problem he or she feels like enough information is present to stop. Because remember, we don't need an answer. We just need to determine whether we can come up with an answer. Okay, so now we see if statement 1 worked, A, D, B, C, E, it's either A or D. Okay, statement 2, she purchased a combination, combined total of 12 pencils and erasers. That's not going to work. Okay, there are many different combinations for that. Okay, many different combinations for that. Now, this is a tough problem, but I want you to see that the principles are very easy. Okay, the principles are not so difficult at all. I'll give you a minute to copy that down. Guys, we may stay a little later tonight. If you have to go, no problem. But I wanna show you one more problem that's very similar to this, so you get a little bit more practice in before you go. Let's take a look at this guy here. Oh, sorry. Let me actually refresh that. You already did that one. And I apologize for the name of this problem. It was like the 3,000 problem we had written. We were sick of consulting baby name sites on the internet, so I had to use my own. Okay, give this guy a whirl. I want you to use what you've learned so far tonight. It's a pretty tough problem, but I think you guys can do it. Let's take it away now. Okay, guys, that was about 2 minutes. And this is a tough problem. And you know, guys, for your sanity, I want you to all remember one important thing. It's tough to see a mixed bag even under one concept in an hour. So don't feel bad, because the way to really do this stuff is to do a progression from really easy to medium, and for some of you into the really hard range. And when you do that, the progression is smooth. Although we're teaching a lot of valuable stuff tonight, just remember for your morale, it's much more difficult to see, you know, 8 or 10 random problems than it is to have, you know, 40 or 50 presented. So just keep that in mind. So if you're getting some of these wrong, don't feel bad. They are very, very learnable with the right approach. Okay, so let's do this, guy. So there's a certain number of students in the class. Could we divide the class evenly into 3 study groups? So why don't we just say T is equal to the total number of students who are in the class. And we want to know, basically, is T over 3 an integer, right? The only way we could divide something into 3 smaller groupings is if that number is a multiple of 3. Okay, so let's look at statement 1. So if the teacher reduced the number of students in his class by 16%, he can evenly divide the class into groups of 9. Okay, so let's decode that into an equation. If you reduce something by 16%, you need to be able to quickly see that what that means is there will be 84% remaining. So after a 16% reduction, there will now be 84% of the students who remain in the class. As Jeff told you, you want to make sure you reduce whenever possible. This simplifies to 21/25 of the total. Okay, and when we reduce the class by 16%, he can divide the class into groups of 9. So pay careful attention, guys. What that means is this value in the blue box must be divisible by 9. Right? Otherwise, you would never be able to split whatever is remaining into groups of 9. Okay, and that helps us a lot, because what we can do, and again here we're working on statement 1, what we can do, guys, is we can say, well, 21/25t divided by 9. And don't let this bother you guys. Watch what I'm going to do. I'm going to say is equal to some integer k. Doesn't matter what we call it. I'm just picking k because it's just a random variable. But k is an integer. Right? If this in the blue box is a multiple of 9, what that means mathematically is we can divide it by 9 and get ourselves an integer, which we're going to call k. Okay, no big deal. So let's flip and multiply. So that's times 1/9 is equal to k. Remember, when you divide by a fraction, you're going to flip and multiply the fraction. And after you do the reduction, what this tells us is that 7 times t divided by 25 times 3 is equal to k. I just remember 3 goes into 9 3 times, 3 goes into 21 7 times. That's how I got 7t. Okay? Well, remember that k is an integer. Okay, we'll take a look. 25, neither 25 nor 3 are going to divide into 7. Okay, and the part of this that we really care about is the 3, right? Because we're really being asked, can he divide this into 3 study groups? And so we'll neglect the 25. Well, what's the only way that k can be an integer here in this problem? Think about it. The only way k could be an integer is if 3 divides into t, because you know 3 does not divide into 7. 7 is not a multiple of 3, and 3 is not a factor of 7. Okay, so the only way for k to be an integer is if t is a multiple, if t is a multiple of 3. Okay, t is a multiple. Sorry, my dogs are going crazy. You can hear them in the background. It's 5 o'clock is their dinner time. T is a multiple of 3. Okay, so with that said, we can go back to the question, could we divide the study group in the class into 3 study groups? Well, we let t be the total, and from statement 1, we just saw that t is a multiple of 3. Okay, so we get a yes. We could divide the class into study groups of 3. Okay, I'll give you a minute to kind of write that down. We're going to use the same logic in statement 2. So while you're writing that down, we'll, for good measure, say A, D, B, C, E. We know that statement 1 alone works, so B, C, and E are out. Okay, let's look at statement 2. Statement 2 says that teacher reduces the number of students in the class by 6%, and after doing that, he could divide the class into study groups of 3. Well, a 6% reduction means that 94% remain. Right? So if you start with t and you reduce t by 6%, you're left with 94 over 100 times t. Okay? And as Jeff told you, reduce that down, so that's 47/50th t. I want you to think about it now, just as we did with the blue box above. If after making the reduction, the 47/50th t can be divided into groups of 3, well, what that means is it must be divisible by 3. So what we'll say is 47/50th t divided by 3 is equal to some integer x. Don't let the variables confuse you. Okay, x is just an integer, just for us to keep some accounting going here. Now notice I didn't pick k. You never want to pick the same variable unless you know the variable is actually equal, in which case you wouldn't be solving for anything. So I'm picking x. X is the k counterpart in statement 2. Okay? So let's multiply by 1/3. So we have 47/50th t times 1/3 is equal to x. And we see that x, remember, x is just our integer. Don't be scared of that. X is 47t over 50 times 3. That's 47t. Okay, guys, again, if x is an integer, what's going on with that 3? It can't be hanging out down there in the denominator. The only way this can work is if the 3 can be absorbed into the numerator. Okay, and what that means is since 3 sure as heck does not divide into 47, right? I'll say it again, 47 is not a multiple of 3. 3 is not a factor of 47, so it won't divide in. It must be true that the 3 divides into the t. If the 3 divides into the t, we conclude t is a multiple of 3. Okay, and if t is a multiple of 3, we go back up to the stem. We want to know, could we divide it into 3 study groups? Yeah, we could. Any multiple of 3 can be broken up into even groupings of 3. Okay, so the answer here is D. Both of these statements alone, or rather each of these statements alone, is sufficient to answer the question. Difficult problem, guys, but I wanted to show this to you. If some of you are shooting for 700 or higher, I want you to see that the difficult questions still are rooted in simplicity. Okay. So sorry for keeping you guys over. I appreciate you coming tonight, and I hope you got some value out of this. If you have any questions, certainly send us an email, give us a call. We'd like to help you succeed any way we can. Jeff, do you have any closing comments?
No, but I sent everyone the feedback form, and thanks everyone for coming. And for those of you that are our students, keep working hard. For those that are not, Scott and I will both challenge you to check out our curriculum and call us with any questions you have about it. We're excited to have as many people use this as possible. So we are always here.
Okay, guys. We'll see everybody next Tuesday. Same time, same place, same channel.
All right. See you, everybody.
Okay. Good night, everybody.